I would like to invite on stage Mr. Hitesh Balwani.
Hello, can you hear me? Okay, so like this is my first time in Gujarat, and I'm quite amazed by the hospitality here. Actually, I've been here for a week. I think I've already gained like 3 or 4 kilos. So, so the topic today is thinking asynchronously, building a serverless event-driven architecture on AWS. A little bit about me. I'm a backend developer at LearnApp. At LearnApp, you can get educated about your finances. I have total 6 years of experience, and luckily half of it in serverless space. So before going through uh, like a technique, like I have divided this talk into two parts actually. The first is like what is the problem we are solving actually. What is an event-driven architecture? What is the motivation behind it? And then we'll have a technical implementation once we have a grasp of what actually we are doing. So before starting, I would like to discuss one important topic is microservices. So when you have a huge use case and there are like lots of people working together, it makes sense to split your use case into different domains, like a user domain, a payment domain, a discount domain, and you have separate teams working on those domains. So what it does is, as an engineer, I am supposed to know about my domain only, and not everything which is going on, which kind of keeps me sane and productive. So what are the advantages microservices give us? It gives us, as I said, domain isolation. So I need to have knowledge about my domain, and I don't suppose if I'm working on a user domain, I don't need to know nitty-gritties of coupon domain or something like that. Agility within a team, productivity, and if we wish some parts of our application to be more scalable, we can have completely different tech stack for a particular microservice. Now, with these advantages, it makes the system complex as a whole. Complex in terms of communications and networking, operations, troubleshooting, end-to-end testing, and data consistency. So, the purpose of this talk is how do we deal with the later part, like how do we simplify it? So this is a simple user sign-up flow. I'm trying to explain through an example. We have user requesting to the user service saying, I want to sign up. The user service performs some business logic, like whether the email exists or not, like different business logic. And once it's done, it calls the messaging service saying, hey, can you please send an email? Once you are done, let me know. I'll send the response back to the user. So this is a sample flow. Now, let's consider some edge cases. What can happen? What if the messaging service goes down? Now, as a user, I won't be able to sign up because the messaging service is down. The endpoint which user service was calling, it has changed, and now it needs some coordination between both the teams to go live, and this coordination can become a little tricky. and more services enter into the picture. So what I'm trying to say is it's not very simple as okay, just calling the messaging service. We need to actually implement some mechanisms uh, in the microservices architecture in order to tackle these issues which I just mentioned. And this design pattern is called as Saga. So I will explain Saga in a very simple terms. Like many of you are backend developers here, right? So how many of you know ACID in MySQL databases? So what is the motivation behind ACID? Like everything is consistent and like the transactions are atomic in nature. So what about microservices? For example, service A is calling service B is calling service C. Now, what if service C fails? So whatever transactions happened in service A and service B, they need to be rolled back. Otherwise, the data is inconsistent. So this is called as a saga. Saga. So it's similar to the ACID analogy which I gave. Now, there are various ways to implement this saga pattern. One is shown on the slide only, where the microservice itself is responsible for error handling and retry. And like everything, like where the code base sits, the logic also sits there. But this can get a lot complicated. So we had quite services like which provided this service and said, okay, we will handle this. We'll handle this error handling, retry, and whatever. You just focus on the business logic. Just pay us money. We'll handle it. So one such service is AWS Step Functions, which is an orchestrator, and it will handle whatever edge cases I just mentioned, and you focus on the business logic, and the orchestrator will take care of the coordination between the microservices. Now this is fine up to a limit. If you have a couple of microservices, it's fine up till that. But as a business, you have different use cases coming in, and you want to make more changes in a faster manner. Then this becomes quite a bottleneck, because the orchestrator is now handling everything, and it becomes a central point of failure. Not in the sense of technically, like if it goes out down or something, but everything is handled through that orchestrator, and whatever change you have to make, you have to go through that orchestrator, and it's kind of rigid, it's not flexible, and you're not able to move. You were able to move faster at the beginning, but once you have gone live and you have different use cases, it's kind of irritating, and like it's kind of pain to move in a speed manner, and it kind of makes us question if we had to do so much things, why did we split into microservices in the first case? If we have so much trouble, we would rather go back to a monolith. So then there's another pattern in the saga which I mentioned, which is called as choreography. So going back to the previous example which I had given you, now look at what is happening here. The user service is now again calling the user is requesting a sign up. The user service is just creating the user. It doesn't know about anyone's existence. It's just independent, and it's kind of flexible, and it doesn't even have even awareness of different microservices. It just performs the business logic, and it creates an event into the void, and it says basically, hey everyone, I have created this user with these details. do whatever you want to do with it, don't bother me. As simple as that. Uh, so this is the main motivation behind an event-driven architecture. Here, like, we are actually focusing on decoupling of microservices. So let's start with an event. What is an event? An event is a message or a payload generated by a service signifying some change in the system. Now, a service creates an event, but we need some kind of technology, a postman, you can say, which will carry this event to the required consumers. It will keep track of what are the events getting generated, who is generating an event, to whom I should deliver this event. So this technology is called a router. So in AWS, we have two such technologies, Event Bridge and SNS. You can go and do a deep dive between the difference. They are quite similar, I would say. But let's go ahead with Event Bridge in this talk. So let's have a simple implementation of whatever I've been discussing. Now the user service does some business logic, validation and all. It inserts the user into the database, and then it calls the Event Bridge SDK command saying a user has been created. Looks quite simple, isn't it? But actually, there are a couple of edge cases here also which we need to consider. So in the previous example, let's go so what if the call to the database succeeds, but the call to the Event Bridge doesn't succeed? So here we have a user going to the database, but we don't have its particular event, and so the consumers won't receive that event. Why is this happening is because these DynamoDB and Event Bridge both are completely independent systems. There is no direct way of doing this task in transaction. So how can we make sure both of these things happen in a transaction manner? So DynamoDB supports transaction. It supports transaction within a table and also in two different tables also. So we can leverage this, and we can create two while inserting a user. We can create okay, first, like this was the first edge case which I said, and the opposite of this is also possible, where the call to the database fails, but you have an event and you are sending an email to that user even though in reality it's not there. So as I was saying, we have the capability of doing things in transaction within DynamoDB. So what we can do is we can have two different items. First is the first user insertion item, and another an event item saying that user created event with these details has been done. So we will insert this additional item in a different table. We'll call this table as an event store. Here is the sample schema I have shown here, where you have the custom event, and in the custom event you have, like, this can change. This can vary according to your needs, but it's just signifying from where the event got generated and what is its actual payload, timestamp, etc. So now we have done this transaction. What now? We need a way to know each and every new item into the event store. And how can we do that in DynamoDB? Can anyone give me an answer? Streams, yes. And here here we are offloading this responsibility to AWS. We will get a new item every time. It's the guarantee by AWS. So it's not us who's getting responsible. Like, we are quite sure we will get a new item every time a new item has been inserted into the DynamoDB. So now, going back to the problem, now we are able to do this in transaction. What can we do here is DynamoDB stream supports Lambda as a consumer. In the Lambda, we can do the put events which we were doing here. And this will make sure that like both of the things are happening in transaction. How does our architecture look like till now? We have the Lambda, we have two different tables, we do the DynamoDB transaction, we have a DynamoDB stream enabled on the event store, and as I said, now we have Lambda, and the Lambda will call the event bridge SDK. This seems, but if this is understood, the next part will become even more intuitive. As I said, this is the final architecture where we have a stream listener, and the stream listener is calling the event bridge. As you can see, the event bridge directly doesn't. We have a SQS in between the messaging service. So we have done this to decouple the speed at which the user service is producing events. We want the messaging service to consume the events at its own pace. So we are able to do that using SQS. This is the final architecture, and here you can see that the user service and messaging service are not talking to each other directly, but they are self-contained. They are like they have this what do you say, proper decoupling, and this is the motivation behind the event-driven architecture, which I discussed. Does anyone have any doubt in this till now? Yeah.
Can't you elaborate Kafka over here? This architecture looks somewhat complex. Since Kafka has the streaming functionality, right? Can't we do the
Yes.
PubSub kind of stuff?
Yes, we can do that also. So there is no specific answer to this. It depends. So the main difference here is in Kafka, the messaging service will have to poll from Kafka. Here it's the event bridge which is taking care of the postman. I would say like you can use it. It's not like you can build it without Kafka. Yes, true.
Like we are using lots of AWS component, right? And it's having its own billing, correct?
Yeah.
Rather we can leverage that platform. It's okay, but that is a minimal approach. We can change this final architecture to that, and that was
So yes, there can be a lot of changes in the architecture. One thing which I didn't mention in this, but I can since we are having the conversation, if you see this stream listener, we can offload that functionality also to AWS. What is the stream listener doing? It's just calling the event bridge API, right? So does anyone know the new technology? How can we offload this to, we don't need to write this code also. Anyone aware? So we have this technology called event bridge pipes, and which will with that there's a direct connection between the event store and the SQS. Yes.
Before I ask my question, I want you to answer that question. The reason why we need Kafka is that because here you are doing server, right?
Yeah.
you are
How could I forget? Sorry.
you are automatically connected. You don't write a code to send it to Kafka document. If you use Kafka, you will have to do that, right? You have to write code. You are define the purpose of serverless. Yeah. And the question I wanted to ask is on the DynamoDB streams, are we having the guarantee of the sequence?
No, and here, there is no guarantee that it will be processed in sequence, and in most of the cases, we don't need this guarantee. But if we need this guarantee, then we can use SNS FIFO. It will be a little expensive, but that's our requirement, right? And that's also serverless. Yeah.
So, can't we use can't we use MSK for this?
Can you speak louder?
Can't we use MSK for this? MSK?
MSA,
MSK.
MSK.
Yeah, managed services for.
It's a similar question. Again, it will be Kaspa, right? So same question. I think
Yeah, but
you can use it.
yeah, it would be serverless, right? I guess.
No, I don't think it's serverless.
The whole purpose was to reduce the cost.
Yeah.
Managed service for Kafka is really costly.
Yeah.
People will not be able to.
And I don't think it's serverless. Correct me if I'm wrong. Yeah.
MSK, I think, is also optional, but yeah, that is.
Yeah, they manage it. Yeah. Okay.
Whenever you have like lot of streaming requirement, then you can go for MSK or MSK.
Like a click stream, basically, not within the communication, but like a click stream you have to implement. Of course, like again, I would reiterate, like there is no specific answer like this is the architecture which you should implement. This is a sample architecture which I have implemented, and your requirement can change accordingly. Yeah. Anyone has other questions? Yes, we still have time. Yeah.
There are two SQS they are there. One is there and one is near to 5.5. DB.
Are you talking about the two SQS?
The main one.
Yes. So in DynamoDB stream, if you don't put a SQS, it will. If something goes wrong in the stream listener, it will keep retrying, and it will not be nice. So you just put it in the DL queue. It's a dead letter queue. Basically, if something goes wrong in the stream listener, it will put into the DL queue. Any more questions? Yeah. Yes.
Yeah, so thank you for the good talk, first of all. And in an event-driven architecture, I believe that one push event can have multiple consumers, right? So let's say like we have messaging service here, and we have 4 other services consuming that event, and out of that 5, let's say 3 were successfully executed, and 2 were not. So how do we keep a track of unsuccessful consumption of events?
So here we need to implement basically the service which went wrong. It needs to retry the event. It needs to call, okay, this event, I was not able to handle it. Can someone please send it? So here, as you see, the event store is not only ensuring the transaction, it is also an audit trail. It's like a stored into the database. So we can have some mechanism for to fetch the event which went wrong from the event store.
Okay.
Yeah, I think that we'll move ahead. You can of course contact me here if you have any more doubts. I would like to give credits to my CTO with whom I'm just a medium here, to be honest. So I was lucky to work with him and implement this architecture. We already did Q&A. So if you want to know, like here we discussed what is event-driven architecture, and we went into the technical implementation. If you want to know actual use cases which were solved using this, and think about it, how would we do it in a traditional manner, which I discussed, you can follow me on my LinkedIn or my blog, and it can give you a better idea of, after understanding the use cases of the event-driven architecture. Yeah, thank you.